There is one numerical method that is needed on the A-level mathematics course for integration, and that is the trapezium rule. And this is necessary because there are many integrals that we cannot compute. Even though this function here, this integrand, e to the x squared, is made up of functions that we can integrate, okay, e to the x and x squared, we cannot integrate the combination of these. And this is not alone. There are many, many functions which we cannot integrate. Unlike differentiation, where we can always chain it up and differentiate. This is why integration is often so much nastier than differentiation, because there are just many functions you just cannot integrate. There's no way to do it. So e to the x squared is one of them. We've got sine of the log of x. We've got the square root of sine x. These two types of integrals are referred to as elliptic integrals. These are nasty beasts that come up quite a lot in high-level maths, which we just cannot analytically solve. There's no analytical function that we can write which represents this integral for a general theta value. So we employ numerical methods to approximate such problems. And the trapezium rule is one such method for approximating definite integrals of a function. One would require a method when the integrand cannot be integrated analytically. So what I'm going to do in this video is I'm going to derive for you where the trapezium rule formula comes from, and then we're going to have a look at using it, and then we're going to have a look at when it overestimates and when it underestimates. So first of all, how does the trapezium rule work? Well, it's called the trapezium rule because what it does is it approximates the area under a curve by summing up the areas of a number of trapezia. So what I'm doing here is I'm taking this just general function curve and I'm just picking some x values, which I can evaluate the function. I can evaluate the function at all of these because this is a known function, y equals f of x. So I can get all of these points, and if I join the tops of these together, then I will get a number of adjacent trapezia. Trapezia being the plural of trapezium. So here I've chosen 5 x values, and that is going to give me 4 trapezia. Okay, 4 trapezia. So this point here is going to be the point, I'm going to call it x0, y0. This is going to be the point x1, y1. This is going to be the point x2, y2, then we have x3, y3, and then this will be x4, y4. And what the trapezium rule does is it adds up the area of that trapezium with the area of that trapezium, and then the area of that trapezium with the area of that trapezium, and it adds those 4 together, and that approximates the area under the curve. That will approximate the integral, and the integral in this would be between x0 and x4 of f of x with respect to x, and it's a way of approximating that number. The error, we can see that this trapezium is under the curve, so that's going to be underestimate, but these trapezia are all over the curve, so they're all going to be overestimates. So we don't know if the overall answer to this case will be an underestimate or an overestimate. It depends on the proportions of these 3 to that as to what's going to happen. Okay, but we'll have a look at overestimates and underestimates a bit later on. Okay, so how do we calculate the area of this? Well, we're just going to add up the area of these 4, in this case trapeziums, or trapezia. So the area of the first one is a half times the perpendicular distance, and just to keep things simple, what we do is we keep the perpendicular distance consistent across all of these trapezia. This is the perpendicular distance. These are all the parallel sides to the trapezia. Okay, those are all parallel, they're all vertical lines. So the area of the first trapezium is going to be a half h times the sum of the 2 parallel sides, and that has a height of y0, and that has a height of y1. So y0 plus y1. And then the next trapezium will have a half times h times y1 plus y2. And the third trapezium will have a half times h times y2 plus y3. And then the last trapezium in this case will have half times h times y3 plus y4. So that's each trapezium. Now if we add all of those trapezia together, we can factorise out the half h, because that is common to all of them, half h, half h, half h, half h. And then in the bracket we're going to have y0 plus 2y1 plus 2y2 plus 2y3 plus y4. Okay, we can see y1 appears twice because it appears there and there. y2 appears twice, it appears there and there. y3 appears twice, there and there. And then y0 and y4 both only appear once. And that's because these two edges are only used in one trapezium, whereas all of these three edges are used into two trapezia each. So what we tend to do is we just put the first y value and the last y value at the beginning, and then we do 2 times the sum of the other y values. That's 2 plus y3. That's the trapezium rule formula for 4 strips. Now, 4 strips was chosen at the beginning arbitrarily. You could have had any number of strips. We could have had 1 strip. We could have had 20 strips. We could have had 2,000 strips. It really is the choice of the person executing the method. So to generalize this one step further, what we do is we say the integral from a to b of f of x dx is approximately, because it is an approximation, the half h into y0 plus yn plus 2 times y1 plus y2 plus ... plus yn minus 1. And that is the trapezium rule formula. Now I've put squiggly brackets here, but they're just normal brackets, okay? It's just used to differentiate the pairs of brackets. So in short, it's a half times the perpendicular distance into the first value plus the last value plus 2 times all the other values. Now I know it's got y2 here, but if n is 2, then actually y2 would be here, and the only one that would be in there would be y1. Okay, so just be careful with that. I know it says y2 there, but it could be out here if you're using 2 strips. Okay, but that's the formula, and that's what we're going to be using in this video. Okay, let's have a look at a couple of examples then. Right, so here we have the graph y equals e to the minus x squared, and we're going to use the trapezium rule with 2, 4 and 8 strips to approximate the value of the integral from 0 to 0.8 of e to the minus x squared. Okay, so what we're going to need to do is we're going to plug into the formula, and I'm going to say T2. Okay, this is the trapezium rule with 2 strips. This is equal to half times h. Now, if I'm going to do 2 strips, then each strip is going to have a 0.8 base, because the whole thing must be 0.8. So half of that is 0.4. So it's going to be 0.4 to there, and then 0.4 up to there. So h is 0.4. So that's half times 0.4 times, then we've got the first y value. Now the first y value is going to occur when x is 0, because I'm going from 0 to 0.8. So that's e to the minus 0 squared, plus the last y value. Now the last y value is going to occur when x is 0.8. So that's e to the minus 0.8 squared, and then plus 2 times all the other y values. In this case, the only other y value is 0.4. Okay, so that is the calculation that I'm going to be putting into the calculator. Right, so let's get the calculator out. And T2 is going to be a half times 0.4 times, and then I've got e to the power of minus 0 squared, which is obviously just 1, plus e to the minus 0.8 squared, and then I've got plus 2 times, and then in there I've got e to the power of minus 0.4 squared. Push equals, and there's my approximation. Okay, so approximates my integral. and that is going to be 0.646316. Now, usually a question would ask for a certain degree of accuracy. I'm going to do everything to 6 decimal places for this video. Okay. All right, so that's T2, that's with 2 strips. Now T4 with 4 strips. Again, we're going to have a half times h, but h is now different. So when we had 2 strips, we took the 0.8 and we divided it by 2 to give us 0.4, but now we want 4 strips, so actually h is going to be 0.8 divided by 4, which is 0.2. So h has changed, so just be careful with that. Times, and now we're going to put the first value in, which is the same as before, plus the last value, which is the same as before, plus 2 times all the other values, but this time we've got e to the minus 0.2 squared, plus e to the minus 0.4 squared, plus e to the minus 0.6 squared. So we've got, because we've got 4 strips, we've got y0 and y4 out the front, and then in here we've got y1, y2 and y3. Whereas on the previous case, we had 2 strips, so we had y0 and y2, and then y1 was in the bracket there. And we can see we've got 1, 2, 3, 4, 5 values for 4 strips, and here we had 1, 2, 3 values for 2 strips. And there'll always be n plus 1 values for n strips. Okay, so rather than writing it out again, I'm actually just going to modify this line up here. The h value changed from 0.4 to 0.2, so just update that. The first value and the last value are the same, so I can just keep those there. And then in here, I'm also going to get an e to the minus 0.2 squared, and I'm also going to get an e to the minus 0.6 squared. Okay, so my x values will be 0, 0.2, 0.4, 0.6, and 0.8. Okay, to split the 0 to 0.8 strip up. So that gives me a new approximation, which is going to be a better approximation generally. Okay, if you increase the number of strips, you get a better approximation. So that's 0.654851. And then finally, T8. So this time we're going to need 9 values of y. So h is 0.1 now. So it's going to be a half times, h value will be 0.1 because I've got 8 strips, times, and then again we're going to have e to the minus 0 squared plus e to the minus 0.8 squared plus 2 times e to the minus 0.1 squared plus e to the minus 0.2 squared, all the way up to e to the minus 0.7 squared. Okay, and then 0.8 squared is out the front. Okay, so again, just modifying this, I'm going to change the h value to 0.1, and then in the bracket, I'm going to pop in my 4 new e values at 0.1, 0.3, 0.5, and 0.7. So that's e to the minus 0.1 squared plus e to the minus 0.3 squared plus e to the minus 0.5 squared plus e to the minus 0.7 squared. And there we go, it's a new approximation, and that is 0.656966. There we go. Okay, so there's my 3 approximations for this integral. There it is, this integral here. So I've got this one, this one, and this one. We can see that the numbers are getting, well, first one got smaller, then it got bigger again. So it's neither an overestimate nor an underestimate. We don't. Well, it's one of them, but we don't know which. This is going to be more accurate than this, and this is going to be more accurate than that, because we've included more strips. Okay. All right. Second example. F of x equals the square root of 1 minus 3/4 sine x, and initially we're asked to complete the table. So what we're going to do, I'm going to go into table mode on my calculator, because that's just going to make it easier to calculate. So menu, table mode, delete anything that's in there, don't need that. And my function is going to be the square root of 1 minus 0.75 times the sine of x. And we must make sure we're in radian mode, because we're using calculus essentially on trigonometry. So you have to be in radian mode. So make sure you're in radian mode. Okay, the values I want to evaluate this function at are 0, pi on 4, pi on 2, 3 pi on 4, and pi. So I'm going to start at 0, I'm going to finish at pi, and I'm going to go in steps of pi on 4. Table. Okay, we can see that when x is 0, y is 1, which is good. They give that in the question anyway. When x is pi on 4, I've got 0.685325. When x is pi on 2, I get a half. When x is 3 pi on 4, I get the same number again, 0.685325. And when x is pi, I get 1 again, which again was given in the question. Okay, so that's the table. Find two estimates for the trapezium. We're using the trapezium rule for this integral, using 2 and 4 strips. So using 2 strips, I'm going to say T2, that is going to be a half times h. So using 2 strips, I'm using that value, and that value. So the h value is going to be pi on 2 times the first y value plus the last y value plus 2 times all the other y values, but there's only one other y value there. So I've got 1, 2, 3 pi on 4. So go into computation mode, 3 pi on 4. That gives me an approximation of 2.356194 to 6 decimal places. And then T4 is that's going to be pi on 4 times, again, first value plus last value plus 2 times all the others. And now I'm using all of those. So that's 0.685325 plus a half plus 0.685325. And I can plug all that into my calculator. So I'm going to get half times pi on 4 times 1 plus 1 plus 2 times all the other values, which I had, well, I should really use the exact value, shouldn't I? So that was the square root of 1 minus 0.75 times sine of pi on 4 plus a half, and then plus that again. I will actually write it out. So it's 1 minus 0.75 times the sine of 3 pi on 4. So that gives me an approximation of 2.254603. Okay, a couple more things before I finish. I want to talk about when the trapezium rule overestimates or underestimates. So here I've got one curve. So it does that. But what we can see is that these trapezia, they are all under the curve. So we're missing off this area, we're missing off this area, we're missing this area, and we're missing that area. So this is going to be an underestimate. Whereas on this curve, if I draw some trapezia on it, we can see that the trapezia are all above the curve. So the trapezium are going to be more than the area under the curve. So this is an overestimate. And this top case occurs when the curve is concave. That is, y double primed is negative because the gradient is decreasing. And this occurs when the curve is convex. That is, when y double primed is positive. Okay, I've got one final question before I finish. Use the trapezium rule with 4 strips to approximate this, which is the integral from 0 to 4 of the log of x plus 1 with respect to x, and is the approximation overestimate or underestimate. And over here we can see a graph. So let's answer part A first. We're doing 4 strips. So it's going to be a half times h. So we're doing 4 strips and we're going from x is 0 to 4. So therefore h is 1. Times the first y value. Well, the first y value is going to be when x is 0 because we're going from 0 to 4. So that is going to be the square root of log of 1. And the last y value is going to be when x is 4. So that's the square root of log of 5. Plus 2 times all the others, or the sum of all the others. So that's the square root of the log of 2. plus the square root of the log of 3 plus the square root of the log of 4. Put all that into the calculator. So I'm going to get half times, log of 1 is just 0, so it's the square root of the log of 5 plus 2 times the square root of the log of 2 plus the square root of the log of 3 plus the square root of the log of 4. So T4 is 3.692430 to 60p. Okay, 3.692430. And part B, is this going to be an underestimate or an overestimate? Well, if we see the curve here, the curve is concave. So it's a concave curve. So it's going to be an underestimate. And it says to justify the answer, and I would say because the curve is concave for x is 0 to 4. And you could double differentiate this to prove that it is concave, but there's no need to. We are given the graph for that very reason. Okay, so it's underestimate. The calculators, they can actually calculate this exactly, well, I say exactly, to a high degree of accuracy. So if I square root the natural log of x plus 1, and I integrate that between 0 and 4, then the true answer to this accuracy is 3.8866, which we can see is higher than this. So we can see that this approximation has underestimated the actual answer. Okay, it's underestimate, it's fallen short, and that's because the curve is concave. Okay, that's the trapezium rule. Thank you very much.